Hello everyone. In this video, I'm going to go over the integrals of some trigonometric functions. I'm going to go over some examples. Um, the first example, I would like to say first, integral or indefinite integral is just the antiderivative of the given function. So for example, when you look at the derivative of sine x, its derivative is given to be cosine x. And in the same way, if you take the derivative of cosine x, that's going to be um, negative sine x. So in this case, we're going to be going backwards. So that means if you take the integral or antiderivative of cosine x dx, that's going to be sine x plus the integration constant. And if you take the antiderivative of sine x this time, it is going to be negative cosine x plus the integration constant. And you can do it similar way. You can just say, hey, antiderivative of, for example, secant squared of x dx will be simply tangent x, tangent x plus c. And if you take the antiderivative of secant x tangent x dx, you will get the secant x plus c. I'm going backwards. Now, derivative of tangent is secant squared, and derivative of secant is secant tangent. So I just ran it in the backward direction. So let's go into some examples. Of course, we start with some basic examples. For example, what is the antiderivative of cosine of 9x which is going to be written as integral cosine 9x dx, indefinite integral. So how do we work that out? You see, we have a u substitution here. U will be 9x, and then du will be 9 times dx. But I need to write dx in terms of du, so I divide both sides by 9. So du over 9 will be simply dx, which is right here. So let's rewrite the integral. Now cosine, I keep the cosine same. 9x was u as we defined in substitution, and then dx will be du over 9. du over 9. Now, as you see, we got an integral in terms of u, and that's a constant, so I can take that out. 1 over 9 integral cosine u du. Now, I know the antiderivative of cosine u, which is simply sine u. So it's going to be 1 over 9 sine u plus the integration constant. But remember, we started with x, and we have to end up with x. That's why we have to rewrite it back in terms of x. So that's going to be 1 over 9 sine of 9x plus c. So that's how we find the antiderivative of cosine 9x. As you see, like you use a substitution here, I'm going to be going over like basic examples. So this was just one of them. And then the next one that I have, let's change that a little bit, that substitution a little bit. I'm just going to make it a definite integral. Like for example, what about 0 to pi sine 2x dx. So you can solve it in the same way, but this time you need to plug in pi and 0 and subtract. We're going to do it in the same way. Like I have the substitution, u equals 2x, and then du will be 2 dx. So I have dx here, but I need to write in terms of du, so that's going to be du divided by 2 equals dx. So let's rewrite the integral. I'm not going to change the boundaries. You can, but I just prefer this example to plug them back in at the end when I got my antiderivative. So I got sine u du over 2. And from similar to the previous example, you're going to get 1 over 2 negative this time, cosine of u. I don't put plus c because it's a definite integral. I'm going to plug in values at the end. So my final answer in terms of x will be -1/2 and cosine of 2x is going to be evaluated from 0 to pi. That's what we have. So we just plug in the values. So you can take -1/2 out, plug in pi, that's going to be cosine 2 pi minus cosine 0. I can take out a constant, but cosine 2 pi is 1 and cosine 0 is 1. So 1 minus 1 will be 0. So for the answer, we'll get 0. So this is similar example, just simply given in terms of, given as it, when we have a definite integral. So let's go to, I'm sorry, let's go home. Let's go to second page. Sorry. Go to second page. So we can have some space here. Now the other example that I'll just go over, something really similar. I have 3 more examples for you. Cosine to the third x sine x dx. Now this example, what you need to do is like look at cosine and sine, two functions given in there. Can I write one in terms of u and the other one can be used for du? That's what I'm looking at, like a u substitution. As you know, for the u substitution, when you call an expression u, du must be in there in the term that's left. Now, if I say sine to be u, well, that may still work with some trig identities, but I have cosine to the power 3. But if I say cosine x to be u, then sine x is right here, which is the derivative of cosine. So that means that substitution will work. So if I write u equals cosine x, as you see, this portion will be simply u to the 3. And du will be negative sine x dx. Be careful, I'm taking the derivative here. I'm working with differentials. So this du will be negative du. This sine x dx will be negative du because du is negative sine x dx. I hope this makes sense. So it's kind of like the remaining portion becomes du. So if we rewrite this integral, I can pull negative out. I have u to the third du. As you see, this is like a power of u. So it's like a power function. So I take the entire derivative by adding 1 and divide it by the exponent that I got. So it's going to be negative u to the 4 over 4 plus c. So I got this. It's going to be negative cosine to the 4x divided by 4 plus c. As you see, this is like another way of substitution. When you have multiple functions, this is what you can follow. For example, if this was sine to the 4, that was cosine, still you can use the method that I did. So I have 2 more examples. So antiderivative of cotangent x dx. This is a little bit interesting. We need to use that identity for this one. By the way, you can always pause and just work on the problem, try, and then look at the solution. So cotangent x can be written as cosine x over sine x. And as you see now, if I call sine x to be u, cosine x dx will be du. So kind of like this. If sine x is u, the derivative is cosine x, so this portion will be simply du. See? So the denominator, if that's called u, then you look at the top, this is kind of in the way of substitution. So we got 1 over u du, but this is ln absolute value of u plus c, right? Antiderivative 1 over u is ln absolute value of u. So we got the answer, ln absolute value of sine x plus c. So in a similar fashion, you can try to figure out the antiderivative of tangent x. This is something that you may just take a look at. You can practice. This is just another one. Now, one more example, just last example I'll go over is the antiderivative of x times secant squared 4x squared dx. Now take a look at this. I have secant squared. I know antiderivative of secant squared is tangent, but inside secant squared, I have 4x squared. And if I take the derivative of 4x squared, I have x, like 8x dx. And I have that x right here. And I have that dx right here. So maybe I can try that. Like, let's say u equals 4x squared. And see what is du. That's going to be 8x dx. So we have du. No. Now, as you see, we have x dx left in here, kind of like this. If you write secant squared x, secant squared 4x squared, then I have x times dx. This portion becomes secant squared of u, whereas this portion becomes du over 8. As you see, I can pull out 1 over 8, and then I have secant squared of u, du. But I know this antiderivative. This is tangent u. So it's going to be 1 over 8 tangent u plus c. So I hope this makes sense. So you're kind of like looking at something outside in the leftover portion, which gives you the derivative or a multiple, like a constant multiple of the derivative of the function that's what you call as u. So you write it back again, it's going to be 1 over 8 tangent 4x squared plus c. Here, the major point is that I have 4x squared inside secant squared, so I know secant squared u is antiderivative tangent u. So can I use the leftover, which is x, and dx to write my du, which is I can, because the leftover portion is like 2, because the du is simply 8x dx, and what I'm really looking at is x dx, which is going to be simply du over 8. So that's just x dx. So I hope these examples are clear. Thanks for watching. Bye.